guys seem happy? Enjoying the nice weather? Is that why we're so lively? I think we might have one more little cold front in the next couple of days, and then we're probably on to nice weather for the season. I've been caring for a bougainvillea plant. If it freezes, it dies. So I have to actually watch the weather pretty good. So far, so good. But okay. So anyway, hello and welcome. So I forgot to mention this last time, but I did talk with the academic programs abroad director about potential other times to do a Nicaragua trip. I was thinking that maybe over the summer that could be possible. She was as well, but turns out the organization down in Nicaragua, they don't have any openings. They're booked full for the summer, so that's not a possibility. Even though technically a graduate could potentially reinstate their enrollment to participate. It also sounds like they're not really interested in doing something that's not for course credit, so it would have to be tied to a class like this in some way. I feel like that was not the case with the former director, so I think maybe they'll update that eventually. But at any rate, I think possibly over fall break. So if you guys are here or would be around, how interested, by a show of hands, would you be in considering going to Nicaragua during fall break? Some, if you're here. If you knew you were going to be here, let's say continuing as a student, would you be interested? Just kind of as a, okay, so thank you. And I hate that it didn't work out this semester, but trying to figure out what might work in the future. And certainly I'll let you know, and I would do is if that works out, I would email to advertise to this the same course, because I typically have access later. Even if you graduated, maybe you have the emails forwarding, something like that. You'd get to know, and then potentially we could bring non-LSU students or let you travel with us, right, to participate. So, okay. With that out of the way, I left you with sort of a participation homework assignment to read this article. Part of me wishes I gave you a little more specific instructions on what exactly to pay attention to, but I think that I'm going to give you most of the credit just for participating in the quiz anyway, so I don't feel too bad. And also, I think it's a good place to start thinking about how do you actually approach literature to find some sort of information, right? So I talked to you a bit about this stuff in class, but I didn't cover every single specific detail about it. And so maybe you want to know, well, how good at virus removal is it? Is it going to remove any viruses? Is it going to be 90%, 99%? What is it going to do? So you might have that type of question in your mind when you're doing your research papers, and so this would be a great lesson, so to speak, on how to deal with research articles. And I would always recommend first taking a look at the abstract. You might not understand everything that's there, right? I don't even understand everything that's there in the abstracts when I look through them. That's something that happens very commonly when you're looking at academic research. There's a whole language ascribed to this particular topic. If you get into coagulation, sedimentation, and interparticle dynamics, it's kind of a language set that you have to learn. If you get into some other field, it's a different language set. You go over to computer engineering. They have their own language set, right? Not to mention computer languages. So if you think about it like a language, it makes sense that there's going to be vocabulary that just, okay, I don't know what that means. But by starting with that approach, you can start piecing together, oh, it's referring to something in light of this, so maybe I really need to figure out what that one particular word means. Maybe if you didn't know what a coagulant was, you would start there and look that up and figure that out. So the abstract should give you an overview of what they did and what happened. We'll probably give you the highlights and give you almost enough information to know kind of what the paper is telling you about. Depending on your level of interest / how much information you need out of it, that's going to kind of tell you where else to look. Probably look in the conclusions. It'll expand on the abstract in terms of really what they found. But if you needed to know how they did something, if maybe that's what you're looking for, is like, oh, did they use this method, maybe you're working in a research lab and you're trying to figure out how to do something, maybe it's a senior design project, then you probably know something about it already and you're looking for extra help, and then you might check the materials and methods, right? So that might be one thing. For what I was interested in you getting to understand the system and Moringa stuff, maybe you could extract some info there, but more likely I was thinking you'd take a look at the abstract, maybe the intro for a little more context. Especially the last paragraph of the intro tends to be very helpful to understand really what the paper is about. Typically an introduction, and this can be true for your papers as well, your introduction is going to be context leading up to why what you're going to say matters, right? So you're going to build up the story. This is known, that is known, but researchers really haven't delved into this, therefore we did this paper. That's kind of an introduction, and that last paragraph typically is, therefore we did this. So if we look at this, it starts with the present work focuses, so it's context, 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 now here we are with this paper. You'll see that structure almost every time. So that kind of gives it a little bit more. They talk about a few different aspects of it. And this is kind of my approach when I review literature. A lot of times I'll then go and skip. Maybe I'll scan the figures to see if they mean anything to me right away without further investigation. And then I'll head down to, typically the conclusions, and this particular paper also had implications for water treatment practice. So I think both of those spots would have been great sections to focus on, rather than try to read every single word in the paper. Because I didn't tell you not to do that, but I probably should have told you not to do that, because that's going to take a whole lot more energy than is going to be worth for your time to extract information out. So you'd be much better served to read parts and then go and look at the other parts as needed to understand more and more. So it's not like a book where you read straight through necessarily. Okay, so with that in mind, I'd like to have you do the Kahoot, ask you a few questions, and again, you're getting most of the credit for participating, so it's only a small bit of pressure, okay? Can you just let me do it, please? Okay, so join up with your 8-9 number. I'll talk more about the research paper and kind of talk about EndNote, some other presentation tips and stuff next time, because we'll have your presentations will occur a week from today. So that'll be just short presentations. Here's my thesis statement, enunciate it, tell the class, along with your introduction drafts, right? So, and when I say introduction, I really mean that introductory paragraph. Will be due a week from today. So you'll submit those on Moodle, you'll come to class and make your statement, give it to the class, and I'm also going to have, essentially, we'll have you divided into the groups that we selected with the Google Doc, and I'll have, within your groups, I'll ask you to give each other feedback for certain things about your tiny presentation. 20-second presentation, you'll get a little bit of feedback there. Okay, anyone need a moment to get in still? All right. So first one doesn't actually count. I just want you to be honest. Did you read the paper? And like I said, I'm going to just not even look at this one. I'm just, this is survey mode. There's It's, oops, I forgot, I skimmed it. You read the juicy parts, or you read every word? Is what I'm asking. Okay, so we've got 9 overachievers. 10 of you did exactly what I was hoping you'd do, and 4 of you are forgetful, we'll say. Okay, there you go. Or maybe that was 9 liars that wanted that more credit. No, I'm kidding. Okay, so first serious question: what is the supposed method of particle destabilization by this moringa extract? I'm so sorry. I was trying to make it better. There you go. Okay. First one would be changing ionic strengths, adsorption, charge neutralization, interparticle bridging, or seed sites for precipitation. Of course, when you're doing your own research on a topic like this, you'll have this question for yourself, and then you'll have to go and find it in a paper, right? So that quizzing you on this is a little bit backwards. Hopefully, I can help show you the way of things. But it does look like a lot of you read enough, perceived enough to catch that. So that's excellent. So it was that adsorption and charge neutralization. If we were to go up to the introduction, you'll probably find it elsewhere as well. But towards the end of the introduction, they were talking about it, and they said the mechanism of coagulation is believed to be adsorption and charge neutralization, and they go on to kind of describe that in a little more depth. Another helpful hint is looking at the first and last sentence of a paragraph can kind of tell you what it's about, at least, and how the narrative is flowing. That means, by the way, when you're writing, you should try to do the same thing. Try to connect your ideas, connect your paragraphs using those first and last sentences to help even yourself to think about what you're writing about, right? If you start that way and say, okay, this paragraph's going to be about this stuff, and then the next big topic I want to write about that other stuff. That's going to help you fill them out appropriately and make sure they're connected rather than just being random topics here, there, and everywhere. Okay, I'm going to try to just adjust it now and see if I can get something. Okay, we'll try that. All right, true or false? The moringa extract provided removal of over 90% of MS2 viruses. Okay. Answer to this one was true. This was, if you took a look in the abstract, it actually mentions it there in terms of saying decreased the viable MS2 titer by 1.3 logs. So there's a few terminology issues there, right? So a titer, that means really just the concentration of how many viruses are in a sample of water. The viables, meaning MS2, these bacteria that you can actually grow if you give them the right host. And then the log here, you guys should know, 1.3 log, that means a 1 log removal would be 90%, right? So above a 1 log, that's more than 90%. And that was repeated in a couple spots, so that's where you get that information. All right, last question then. Which of the following is not a concern for the residual organic matter that you end up adding when you're using a seed extract, this particular seed extract? So first one would be toxicity of the compounds, then interfering with disinfection processes, and allowing regrowth of microbes after disinfection, or last, substrate. It might act as a substrate for disinfection byproduct formation. So I'm asking which is not a concern. So 3 out of 4 of these are a concern, according to the paper. Okay, so the correct answer here was toxicity of the compounds is not mentioned really anywhere. Let's see if there we go. So that was the correct answer. The other parts were specifically mentioned as considerations that could potentially be problems, including adding materials for disinfection byproducts. Now, I ought to do my due diligence here and check if the word toxic is in here. It's not, so that's good. Because I kind of assumed that when I was reading through it that I didn't see it, and then I was making a quiz, and then I was like, okay, well, I'm just going to assume that wasn't mentioned as a potential issue, so that's good. It did not lead you astray as I maybe could have accidentally. Okay, so hopefully that was useful. It looks like most of you got something out of it and responded pretty well there, in case this needs to happen. All right, you can look at, I guess, the top performers here, whoever you are. It actually doesn't really matter how quickly you answer, it just scores it that way. So there you go, whoever that is. All right. Okay. So I think I covered all of that. Yeah, so on the 23rd, that's when the thesis statement is due, and your introductory paragraph will be due on Moodle. I'll make sure to have an assignment posted for that, if I don't already, with it dated so that you know to submit that. Moodle will give you a reminder that way. Any questions or comments about the Moringa paper before we move on? Do you find it interesting? A little bit? Okay. What's that?
Similar approach to our senior design project.
Nice. Cool. Awesome. Okay, so today we will talk about that. Oops, don't want a blank screen. We're going to talk about filtration, and specifically we're going to be looking at granular filtration, and we'll pick up on membrane filtration after we do the presentation and stuff next week. So really what I'm talking about with granular filtration, it's not the same as like taking a membrane. So if we take a membrane, we have some particle and we want to remove it, so we pass it through the membrane and it gets stuck on the surface. Right, so that's and then you have clean water coming out the other end. So that would be kind of a membrane approach. That's sort of your coffee filter, right? It's just size exclusion. You could think of a screen porch keeping mosquitoes out, letting the air through, but not mosquitoes, hopefully. So in that sense, size exclusion is not really, well, I wrote it there already. It's not really the thing we're dealing with primarily. It might happen to an extent for larger particles, but what we really care about is actually for a granular filter system is kind of what happens in groundwater. The reason groundwater tends to be cleaner than most other water sources is because it's made up of soil, some sort of granular media. Let's say this is a bed packed with sand here. And inside those spaces between the grains, you have all sorts of adsorption or impaction type processes that can occur. And so when you have water flowing through a porous media in that manner, inevitably a lot of the small particles will stick to these grains of sand or the soil, whatever it is, and be removed. So the theory then is if we have dirty water coming in, we add it on top, and then essentially we'll end up with clean water coming out, is the plan. So that means we're collecting particles in the granular sand stuff. We could do a pre-treatment with coagulation, cause the particles to stick together, destabilize them, then they'll be even more sticky to stick to these the granular media. So that's certainly something that can be done. If we're talking about like a municipal scale system, of course, we'll do sedimentation first and then follow with this. Probably a combination that and coagulation. At any rate, if we're doing it for kind of developing context, we really kind of need to think of the scale and how manageable it is and what technologies are required. So we're going to talk kind of from a large scale, just kind of review the basics of how the large scale systems work, take a look at what a smaller scale unit would look like and kind of consider the cost of transportation, the cost of operation, the skill required, and then think about like, what could you do in a household to make use of sort of a granular approach. Okay. Speaking of households, a Brita filter is somewhat of an example. This is also really focused on kind of the adsorption of chemicals. So you've got activated carbon that does a really good job with chemical adsorption, in addition to it being sort of a granular medium. Okay, so there's a few things that happen. I mentioned this size exclusion or mechanical screening. Not really the go-to approach here. That's not what we're designing it for necessarily, in part because that'll block all the pores and then we can't pour water through it. What we want is for the particles to get stuck more on the inside of the granular media, and then it'll essentially fill with these small particles, and then we can flush it out later and dump that stuff to waste. So we'll have what we might call sedimentation. So inside a little pore area, the particles just falling slowly as it's traveling through, and it sediments onto a larger grain. You could have flocculation occurring, so particles meeting each other since they're drawn into a small space together, and it's a little bit of a mixing type of situation where you're allowing particles to meet and grow larger and then get stuck. You could have interception where as they're passing along, they contact a surface, particles just sort of moving along, and it hits the edge of the sand grain there and gets stuck. So it's intercepted by the grain. Or it could just be that you have impaction. So it's sort of like the sedimentation idea. Your water's flowing through, maybe it flows through kind of quickly, and then it veers off to the side to travel through the pores, and the particle doesn't make the turn fast enough and collides with the sand grain. So that would be, those are the kind of the several different mechanisms if we're thinking about kind of the particle movement dynamics. All of those could cause particle removal in a system like this. And sometimes it actually helps to have a few particles get stuck in the first little bit of time, and then the surfaces will become a little stickier to other particles. So a lot of times when you do some sort of a granular filtration operation, if you clean your system or start with some new fresh media, then you have to run it for a little while before you end up having all the sand grains settled and have maybe them start to be coated just a little bit so they're primed to stick to all the other particles. So it's actually having a little bit of stuff on there is helpful which is one of the reasons why we need to rinse a system for a few minutes before we really get going, typically. So this could look like a column-based thing where you have, and I've got these in my lab, could show you if you're interested. Could be these large columns over here. A lot of times you'll have an open bed with gravity pushing. You can do this column-based things where you have pressurized chambers, you're pushing water through. You can get a little bit higher flow rates through your sand or through your media if you pressurize it that way. You just have to be careful, because otherwise, if you put too much pressure, you'll force a channel through the sand, and then you're getting no filtration, and it's just water passing next to sand, or your granular media. So this might be what a slightly smaller scale system would look like, or if we were to really think about probably the most commonly seen, at least by the public, type of a system, and just go to Google and look at pool filters, because they're almost always a form of granular media. So when you're operating a pool system, you'll have these big cartridge sort of things, you have some sort of a pump, and it's pouring maybe something like a gallon a minute, or some amount of water. It's not super fast, but it's a decent amount of water, so it's going to filter the pool, maybe a full water exchange in a day or two, or something like that. And if you think about it, that swimming pool, that's a fair amount of water. That could, if you're producing that much water for, let's say, a community to drink, that would be a decent amount of water, right? You could probably supply 200 homes or something with a swimming pool every day, if that's the flow rate. So if you were to take a look at emergency response units, which is one of the more common uses of this type of cartridge system, you can put these on a pallet, so you can transport them relatively easily. It's not like you have to make them humongous. You can have multiple cartridges, so if you have to operate them in parallel to have a larger flow, that works just fine. You can take just sand, and then you can have activated carbon, so you can sequence kind of what specifically you're treating, get some control over the treatment that way. But that's going to come at a cost of shipping this media, which is pretty heavy, right? So if you think about 1 cubic meter of sand, might not connect that in your mind with how heavy that is, but that is a lot of mass to move, and you need that media, right? That's pretty much required. Maybe you can source that locally, but you do need careful control over the size in order to control the operation like you want. So there's a few considerations there if you're going to ship it. It's certainly possible, and it is done, but it's heavy for the media, so you're going to have to, at minimum, have the capability of essentially forklifts. So you have to have probably some sort of a semi/truck bed with forklift capabilities if you're going with the media, or you're going to have to source locally, which means you're going to have a way to refine the sand or refine the media. So that certainly may be possible, because essentially you want to control the pore size. So those would be the kind of the considerations for how to establish your media in a system like that. Now, if you had just a very remote area, that's not possible. Maybe you could just set something up where you have several vats of sand or granular media that you can collect there, and you wash out as best you can. Maybe you treat them with heat in kind of a makeshift kiln or something. Maybe that works okay. Maybe that's a better option than nothing at all. So it's certainly something that, it doesn't have to be exactly precise to have something that works or that helps, right? But if you're going to do a carefully designed operation where you know the flow rates, you know the pressure or the the backwash frequency, all of that, you need some more control. The other thing is, these are always going to require some amount of energy at minimum, to add water on top of your bed. So if we take a look at kind of in practice, in sort of a municipal scale system, you're essentially adding water on top of the media bed, and then you're using the gravity as the force to push water through the media, because there's going to be some resistance there, right? So in this case, you add water on top, and it fills to a point where it's going to flow through at some rate. Should have learned all about that in 3110. It's just, it's gravity. So if you're taking that approach, you're going to need either a pump to do this, or gravity, but you're also going to need a pump for backwashing, because eventually the sand and the grains, they get clogged up with all the goo, all the nasty stuff, and you're inevitably going to need to backwash it. Eventually particles will start breaking through and making it through the media if you just keep running it forever. And then it's as if you're not treating it, because then you've collected a bunch of junk, and that junk is starting to come back out into your water. In fact, if you're doing that and you run it for too long, maybe you end up getting dirtier water, because all that concentrated junk, maybe you disturb something and suddenly it's coming out and you have extra dirty water instead of cleaner water, right? So eventually you have to backwash. We can talk a little bit about kind of the mechanics of when and why to do that and review that. So that would be the other concern, is energy for essentially pumping. So you need electricity or some other way of providing mechanical energy to move the water about. Maybe you could do that with a water mill or something clever like that, but you certainly are going to need the ability to adjust the plumbing to backwash when necessary. So just a little comment here. This is sort of a granular media. You can imagine that's what it would look like, something like that. Very fine grains, so you get pretty small pore size. And then in practice, a filtration bed in a municipal plant would look something like this, where it's several meters wide and maybe 10, 20 meters long. And essentially, this guy here, he's working on filling this media bed, and that's something like a square meter of media there, or a cubic meter of media, and it's being lowered in on a crane. And if you do some calculations, you'll realize that's a lot of media that's going to fill that bed, and that's very heavy. So it's very important that this stuff is reused. One of the great things about granular filtration is it's pretty much infinitely reusable as long as you're backwashing appropriately. Okay, talked about that. Kind of a example there. People have been using this for quite some time. We mentioned groundwater, so just a bit of history here on the technology. Back in the 1800s, people started to do what we would call slow sand filtration, really giving enough time for biological activity to consume waste products. So that's mostly wastewater treatment, or potentially, I guess, biological treatment of a gross water source that you needed to drink from. Not a very great thing, but it's going to act like a groundwater system just done on purpose. Since then, we typically use what we call rapid sand filtration, which is kind of what we just talked about, applying enough gravity and having enough control over our pore sizes and enough backwashing to make sure that we can get pretty rapid flow through and get all those particle removal goals accomplished. Okay, so then there's a few terms we talk about when we're talking about operation, which would be filter ripening. I mentioned that first few minutes of operation of a new clean filter, or maybe the first couple gallons you filter in your Brita filter, you get those black particles. That's just kind of your media coming out when you were hoping that it would stay in there, right? So you just need to flush that out for a little while because you have some particles escaping. That's going to happen after you backwash, which you're going to have to do that. Sometimes people will use air to dislodge particles, but you need to flush water as well. to kind of regenerate that filter. A lot of times we'll talk about head loss. That is really meaning a pressure drop. So you have some amount of hydraulic head being applied to your filter. Maybe that's 2 meters of water stacked up on top of it. That's a decent amount of pressure applied to the filter, and you can think of that, how much pressure is required to achieve your goals of how quickly stuff's going through. That's going to drop over time as it clogs up. So that would mean more and more water has to be added to the top of the filter, or more and more pressure if you have a pressurized system. So that's one way we talk about these systems, and one way we identify when it's time to backwash. So one of the things here is we want to know, if we're going to implement a system, how often do we need to backwash it? Well, it's going to depend on essentially the filter's performance. In let's say a disaster relief scenario, we're going to want to know as much as we can about the source water, but we're probably not going to know much about it. So rather than say, okay, well, it's probably good after 48 hours, that's when you should backwash. Instead, we probably want to take a look at head loss and monitor the turbidity. For some municipal systems, maybe a time frame is reasonable. Every 72 hours, they take the filters offline and backwash them. That's not necessarily practical, so as we think about it, okay, turbidity, we know all about that. Essentially, you just want to monitor that in your treatment before and after, and monitor that over time to see, okay, after how many hours, maybe at some point it gets to this color or slight, something like that, then we know we need to backwash, because it should be producing clear water and it's got particles coming through. So interesting ways to measure turbidity. If you're measuring it in kind of a natural water system, you have these Shecky discs. Essentially, you're just looking at how much light is being scattered by the particles in water. So the further you can see a disc like this and distinguish between the black and white sides of it, or edges, that's lower turbidity. So the further you can see. So we can have little light measuring devices that essentially do the same thing and give you a good estimate without all that involved. Okay, so then determining the backwash frequency, then essentially what we want to do is take a look at the different methods. If we're operating some sort of filter and we monitor the turbidity, what it'll probably look like as a function of operation time is, if we say we just cleaned the system and we start filtering water through it, the first few minutes, maybe 20 minutes, essentially what we usually do is we usually say, okay, above this amount of turbidity is unacceptable. We know the filter can produce better water than this, so anything above some line is kind of unacceptable. So this might be our cutoff. First few minutes is right after cleaning is probably going to be above it. And then it'll drop pretty quickly off to some time frame, and so we usually define kind of that drop off as this is the rinse or the ripening phase. We don't want to use that water because it's unacceptable, right? So that all goes to waste, and we don't use it. So then after that, our filter is operating like normal, getting pretty clean water, and then it slowly, the water is decreasing in quality, because eventually particles start breaking through, and we end up saying, okay, well, at this point we really need to stop filtration. And so all of this time then would be production, and we'd cut it off here, so really we don't have anything else, and here's where we would backwash. So that's probably the best way to do it, especially in a situation where you might have variable water quality coming in. Yeah?
How does that wastewater, does that get reintroduced to the system, or is it just gone?
It's a good question. So, and for those online, the question is, what do we do with that wastewater? Does it go back into the system? There was actually if you do that, if you recycle it, what you would want to do is send it through a sedimentation basin because it's full of all these particles. You could sediment a lot, take a lot of the particles out, and then send it back through. But there's a infamous case in Milwaukee where I think they were doing that, and they ended up concentrating a whole bunch of cryptosporidium cysts, so pathogen spores, and eventually that ended up causing a massive outbreak in addition to some other problems. So you don't really want to do that. There's a way maybe you could. So usually it just goes to wastewater for either municipal wastewater treatment, or if you're, maybe in a rural spot, maybe just use it for agriculture, right? That's potential. Question?
When was the cryptosporidium incident in Milwaukee? Because I feel like I read that somewhere.
Yes, I normally assign that in my 3110 class, so
I wasn't in your class, but
right. But so I normally go through, I think it was 1991 or maybe 1989, right? That range, yeah. So it was a big deal. Probably one of the largest waterborne outbreaks that the U.S. has seen, and we didn't really know a lot about cryptosporidium before then. It turns out that it's like a month or two of diarrhea, not fun. It's related to Giardia, or similar to Giardia, which in people, if you think of, there's like hiker's diarrhea or whatever. If you go hiking and drink water that's not very clean, and then you end up with diarrhea for a couple months, you probably have one or the other, cryptosporidium or Giardia. They're throughout nature, essentially, in a lot of animals. So natural waters are often contaminated with it, and it really doesn't require many of them to cause an infection. Many of the pores. But also, chlorine does not do a great job at disinfecting them either. It requires a long time. So back then we knew of it, but we didn't know much about it. So then we learned a lot about it. It turns out that for most people it's like not too big of a deal, but for anybody that was immunocompromised, it was actually very dangerous and did kill people. Because of mistakes, specifically their turbidity monitoring was offline. So it's a good case example of why you really do want to be monitoring your turbidity and have these cutoffs for that. So they had several issues with that treatment plant, several things going wrong, and the first time I learned about it, I think they said they were recycling. The big paper about it was really highlighting the improper turbidity monitoring, and there's a couple other aspects of it. Okay, so I mentioned a time limit. If you operate your system and you know that this happens basically every time, sometimes after like 3 days of operation, and you have the same exact source water that's not very variable, a time limit might make sense, right? Your operators, you just know that you're going to do it every other day, so that means you're taking maybe one set of 2 filters off every day out of 10, and so basically you always have 8 operating and 2 offline for maintenance, or something like that. That head loss limit, that's going to relate directly as well. So if we were to take a look at head loss, essentially if we have a clean system, we'll mark the end of the ripening, and then we have backwash here, and production in the middle. Essentially what we'd have is, again, some sort of a cutoff, but this time there's not as much interesting happening. We just know that a clean filter is going to start maybe something like that, and a dirty filter is going to end up reaching a head loss limit eventually. So if I could intersect it appropriately, that'd be ideal. But so as soon as we reach that head loss limit that we decide on, that's when we would take it offline, and so that gives us some amount of production time. So that's the way we can think of a filter. So any granular filter is going to have some set operation cycle where we have that rinse. That's usually going to be something like 20 minutes. It really depends on how much water, how quickly you're pouring it through. We're going to have production Generally, that's going to be something on the order of a few days, 24 to 72 hours, something like that. So the majority of the time, hopefully, is production phase. And then at the last bit, we're going to have backwash. And hopefully that only takes about 20 minutes as well, something like that. But again, depends on the system. If you have a low flow scenario, maybe you operate longer, maybe it takes longer to rinse and backwash. This is really kind of typical for municipal scale systems, which will also hold true for kind of pressurized systems that you might take for disaster relief. Okay, so I like to show videos, so I often show this one for the backwashing process. I'm going to turn my volume on, but keep it pretty low, and I might mute it at some point because it gets really loud when they do the air purge. Okay, so they've got a granular media system here that they're about to start backwashing. You can see we're starting with an air purge, and so all those bubbles are kicking up this water. And this is a municipal scale drinking water treatment plant. So this is seeing all that nasty, nasty water that's all collected from the filters that are essentially they're treating water, and that's what's being caught. I'm going to fast forward a little bit because that just bubbles for a little while. Eventually stop their the air, and then they purge it. I'm just going to go ahead and mute it. Yeah, I'm gonna mute it. Oh wait, wrong way. Kidding. So that's loud and uncomfortable, obviously. They're just priming the pump so that they can get the air out of it, so then they can put the water, they're primed with water, so then they can push water up through. So it takes another couple minutes. Well, another few seconds anyway. Okay. So they got their pump primed, and you see they actually have a pair of filter beds here that just kind of focusing the camera on one. It's pretty common to operate like that with a trough between them to collect or to distribute. So collect the backwash or to put in clean water through or water to be treated through there. Okay, so now they're starting, I think, to push water through. So we see a lot of air bubbles escaping. Water is rising a bit. Okay, they fast forwarded. And you can see the delightful, I think somebody makes a comment in one of these videos like, you ever wondered how root beer is made? So, I mean, technically most of that's just soil particles and stuff, right? So it's definitely gross, but it's, at least it's not like wastewater gross, right? But this will be treated, most drinking water treatment facilities have a wastewater discharge permit of some sort, because a lot of times they will then have a separate process to answer to your question earlier. That's a lot of water that needs to be gone to waste, so they're going to have that waste product. They're likely going to do sedimentation, possibly some biological treatment, and then discharge. If not, then they're going to have they're going to be paying the wastewater treatment system to take their waste. But typically you've got the operators, you've got the skill, you've got the facilities for the most part, and all the control systems you would need. So a lot of times it makes sense just to treat on site. Okay. So I wanted to share that with you real quick. The color is interesting. Sometimes I'll go on to the, which one's next or whatever, and you'll see different treatment plants doing backflush, and sometimes it's very orange, maybe if they've used alum as a coagulant, or maybe if it's the, in Louisiana here, most of our water systems have lots of sediment, just from the Mississippi River Basin, so most of our soil is really sediment that's accumulated and been transported from kind of north in the country, so it's a lot of fine particles, kind of a dark soil. When I was growing up in Georgia, we have a lot of clay. So it's Georgia red clay is like this kaolinite stuff, and it's red or orange. And so treatment systems there, probably from the natural water, would be like an orange-brown type of a color for their effluent or for their backwash like that. So it really kind of depends on what stuff you're treating. It'll collect a particular color. Okay, so what about household scale treatment using a granular type approach? We mentioned Brita filters. Those are nice to make you feel good about your water, but that's not really a treatment for pathogens, right? We don't do that to treat pathogens. Maybe we do it to remove some chlorine. Maybe we do it just in case there's some sort of other organic materials that you don't want. Maybe you just like the taste better, or maybe it's a placebo effect. Whatever it is, it's not really doing pathogens for you for the little Brita filter. So there are ceramic pot filters. This is a common design that people have kind of investigated and developed to an extent. And the attractive part of using ceramics is, well, first of all, if you look closely at any ceramic vessel that has not been glazed and all that. So if you have some vessel and you look at really the walls here, you're going to have sort of a porous material. In fact, if you have any cookware, like stone cookware, it's essentially ceramic of some sort, and you actually don't want to wash it with soap. You're not supposed to, because you don't want the soap to get stuck in those pores and then to come out in your food later, right? So you're typically going to use them to bake something or cook something with, at a high temperature, so you're not really too worried about getting something that's like, long-term contamination hazard problem. So essentially you just wash it with hot water and something to scrape it. That's what you're supposed to do typically if you have like a pizza stone or whatever. So in this case, you'll notice that these pores can act, if you design it well enough so that there's enough pores, you can actually do filtration through those pores and have sort of granular filtration in that manner. That there's obviously some obvious problems here. That's not a lot of media to go through. If it's allowing water to seep through it like that, then if we consider the pore sizes, the typical pores are going to be larger than bacteria. If you can just let a little bit of water to do that, if that's enough energy for it, the pores are going to be probably upwards of 10 micrometers. Bacteria are about 1 micrometer, so it might stop some bacteria, but certainly no guarantee. Definitely no viruses. So there's a few issues here. You can typically remove larger parasites. So we talked about just sedimentation and the fact that certain types of parasites might just have a lifetime of less than 2 days, and so they'll just decay and die before they get to infect somebody. Those larger ones like that, perhaps you can get some removal. If I'm right about this 10 micrometer, maybe it's more, but if I am right about that, that should remove most Cryptosporidium, Giardia cysts type things. They're a little bit larger, but again, I don't think that would be a guarantee because you probably don't have perfect pore size control. And of course, the trade-off here is if you have too small of a pore size, you either have to pressurize it, in which case, essentially, you have a ceramic membrane there. That gets us into membrane filtration. Or it's just going to take a really, really long time. So one of the disadvantages here, if you set up a system like that, you pour water into it, and then you have to wait 8 hours before you have enough water to use for drinking and cooking for the evening, maybe, right? So it's really a pretty slow process. So some of the pros and cons, you could say local production makes it is a great benefit. I know there was a group in Nicaragua that was working in southwestern Nicaragua that was doing some of these. I got a chance to tour kind of some of what they were working with while I was down there one time. It struck me as not a great option, but better than nothing. That's the impression I left with, kind of seeing what they were doing. It almost felt like it would be much better just to put the energy towards digging a well, like drilling a well properly and protecting it. But of course, an individual village or family is not usually going to be able to afford that on their own, but they could afford a ceramic pot filter, and maybe producing them would be an economic benefit. So definitely some pros and cons. Maybe not the best bang for your buck for development efforts, but they're simple to operate. You pour water in here and then you have a spigot to use later. As long as you keep this larger container that the pot rests in, keep that as clean as you can, it should work pretty well, right? You will have at least a removal of turbidity, so that'll be some benefit there. You'll get rid of some bacteria, larger parasites. Certainly viruses are an issue, bacteria are still an issue. The process itself, you'll get a little bit of adsorption to the sites like you think for our typical granular filtration, but you can't backwash this. So that's going to be somewhat limited, and then it sort of becomes a membrane type of filtration. It does become size exclusion. So this is kind of a crossover between the two technologies, using these granular pores. So there's some benefit. I don't think it's a be-all, end-all, or completely sustainable solution. People have added silver to them. So if you add silver, maybe colloidal silver particles to the ceramics in the process, you can get them stuck on there decently well. And we know that silver has kind of an antimicrobial characteristic to it. And there's some debate about if the silver surface itself, since you can have a bit of a positive charge on that surface, that can disrupt bacteria and essentially ruin their functions, cause them to die. Or maybe it's silver ions that are released into solution, and those are what's causing the antimicrobial property. So in either case, we do have silver ions leaching out into the water. There's a little bit of toxicity for silver, for humans even. It's pretty low and really would require more than what you would even want to add to a ceramic pot filter because of the price. Because obviously we're looking for a cheap intervention here. A very small coating or deposition of silver colloids would be pretty cheap because it's really a really small mass. So you can have a good antibacterial effect that way, but there are some questions about, okay, how long does that last? Does it get fouled up by some organic matter and then it does nothing? Should we be concerned about that toxicity? What kind of pros and cons here? So it seems like that's probably a decent solution to add to it to make it a little more effective against bacteria, but personally I don't think I would count on that. I think, again, I think that other technologies may be a lot better. I have a little image. If you just search for colloidal silver these days, it's commoditized, commercialized, so people are recommending it for all sorts of things for whatever reasons. But it does have some antimicrobial properties for that. So my take is I'm not sure about the sustainability of the ceramic pot filters. Certainly there's some positives there, but especially if you're relying on that with the colloidal silver, I'm not so sure. Just another image here, and really the important operational parameters are that A, you clean this out every once in a while, or probably daily, because that's going to get gunked up inside. And B, you take special care to keep the water and this chamber clean as best you can. And so teaching somebody to operate something like this, first of all, you have to make sure you have a decent seal here so that you're not contaminating your cleaned water. And then secondly, they have to recognize that you're going to have to put water in here and let it drip through that and strain through that for hours before you can use it. So if you want it for dinner time, you start in the morning and you maybe just periodically add more during the day. So one family might need 1 or 2 pots just to comfortably have some water when they want some water. So a few issues here, but certainly something that's better than nothing. Okay, so I think probably save the filtration, the membrane filtration for next time, but there's a few clever ways to get maybe a little bit of extra pressure, maybe just using gravity with a bag like this. I think this is a fancy ceramic pot system where they've got the chamber up here is the pot, and then kind of a clean chamber down there that may not even be accessible. I'm not sure. Probably can clean it. But we'll get into a little bit more of that next time. Any questions, comments before we go? All right, so have a good week. I'll see you guys on Monday.